Thank you very much for the introduction. Today, I'm going to talk to you about a metric, neural network-based metric we developed for the motion compensation, deformable motion compensation in cone beam CT. So I would like to start by thanking all the members in our lab at Johns Hopkins and our clinical and industrial collaborators and our NIH funding source. So cone beam CT has been increasingly used in interventional radiology, such as minimally invasive procedure in abdomen, which includes the transarterial chemoembolization, or TACE for short. So it's a schematic for TACE procedure is shown on the right. And in such procedure, the identification of the small tumor-feeding vessels are very crucial. However, cone beam CT has a relatively low acquisition time, giving the potential for patient movement, and that can degrade the image quality. So the motion in abdomen cone beam CT is deformable and often complex, and it can be results of both a respiratory motion and the involuntary movement, such as the gut movement. There are some clinically used common motion control methods, but they all have their limitations and they do not fit very well into the interventional workflow. So a more effective way for the cone beam CT motion management would be the image-based autofocus motion compensation. And the previous study have shown success in rigid motion compensation, and our previous work has also demonstrated the feasibility in deformable motion compensation using combination of locally rigid motion within ROIs. So here's our framework for the deformable motion compensation. So we start with motion cropping projection data, and after the FDK reconstruction, we will pick a few motion cropped ROIs from the volume, and then we use these ROIs to calculate the autofocus metric. And this metric will be used as the objective function for our optimizer to convert to a solution of 4D motion vector field, which is then fed into a warped back projector with the motion cropped data to finally generate the motion compensated cone beam CT. Now, obviously, the key to success in our framework is this autofocus metric. Conventionally, we have used the image property-based metrics, such as entropy, variance, or gradients. However, they are unaware of the underlying anatomical structures. Previously, there are some studies have investigated the learning-based metrics, including the estimation of cardiac motion model, the reprojection error, and last year in Fully 3D, we present our work on recreating the similarity metric, the visual information fidelity without a reference. However, once we advance this workflow into the deformable motion, there are some challenges. First, deformable motion is complex and non-uniform, so our previous approach of using a single number to quantify the motion artifacts inside the image is not sufficient anymore. And also, since we are working on ROI base, the information in each ROI is limited. So therefore, we need to incorporate some anatomical context into the ROI metric calculation. So therefore, we propose a local context-aware reference-free autofocus metric. So let's start with the similarity metric we want to recreate, the visual information fidelity, or the VIF for short. So it basically calculates similarity between the two images by modeling human visual system and the information loss process. So both the distorted and the reference image are passed through the human visual system channel to compute the information preserved. And the VIF will simply be the ratio of the information contained in the distorted image to that contained in the reference image. However, as mentioned before, this VIF scalar value is just one scalar for the entire image, so it does not provide any local information. Luckily, another study have shown that if we do not sum all the pixels throughout the calculation of VIF, then we can actually preserve the spatial information. Therefore, we can get a VIF map indicating each contribution of each individual pixel to the final VIF scalar value. So put it into the context of the cone beam CT, you can see here we have a deformable motion cropped image with its corresponding reference, motion-free reference image. And on the right, we have the VIF calculated using this pair. And if we want any local similarity information, we can simply crop out a ROI from this VIF map. And so now that we have addressed the local metric issue, now we can move towards getting the context into the metric. So here's our network. We call it a context-aware learning-based VNF, or for short, CADLVNF. So it tries to replace the DLVF map without using a reference image. So here, so the network has two identical branches, but they have their own weights, so they are only similar in structure. So on the bottom, we have the low resolution branch, which takes in a 64 cubic voxel coarse reconstruction with a 2 millimeter voxel size. And it first passes through a batch norm layer and then a cascade of residual block layers, which is our implementation of the residual network. And then once we extract the feature map, we'll feed it into a series of 1 by 1 by 1 convolution layer to finally to get a low resolution DLVF map. And the high branch follows the same structures, but the image was taken from finer resolution. The RI is 64 cubic voxel size, and it was taken from 256 volume reconstructed with 1 millimeter voxel size. So the RI also passes through the similar structure as the low resolution. So how we get the context information in is that for the feature map we extracted in the low resolution branch, we do upsampling and cropping twice to get the contextual information for this RI, and then we will concatenate that to the feature map extracted directly on that RI, and finally passing them together through the convolution layer. So to train this network, we start with the multi-detector CD volume, and with artificially created casters and contrast enhanced vessels. We started by passing the MDCT volumes through our cone beam CT simulation pipeline with and without motion to generate a motion-free scan and motion-corrected scan. And this pair will be used to generate a ground truth VNF map. And then to improve network's performance on clinical data, we also pass the motion-corrected cone beam CT scan to our high fidelity model to add a Monte Carlo simulated scattering and quantum noise. Therefore, we obtain a realistic motion-corrected cone beam CT scan. Now, during the training, a random RI will be taken from this realistic motion-corrected CBCT scan together with the downsampled whole volume into the network to generate a local and the global DLVF map. And it will be, so for the ground truth, we also do the same stuff to extract a local VNF map and the downsample to extract the global VF map. And we use the MSE loss and Adam optimizer to train our network. So once the network is trained, we need to evaluate its performance. So we designed the following experiment to see how well the DLVF will recreate VF under different scenarios. So in the first experiment, we fixed the scanning protocols. Basically, we fixed the KV and MAS for the scan, but we applied different amount of motion with different amplitude and frequency, also the phase shift of the motion. On the next experiment, we fixed the motion pattern to be a moderate one, but we varied the scanning protocols using different KV and MAS. We also applied random phase shift to the motion. And we will use the R-square and slope to evaluate the performance of DLVF to VF by see how they correlate. So here our results are related to different motion patterns. So on the left, we have the aggregated results from all the testing cases, averaged across all the amplitudes, frequency, and phase shift. So the x-axis is the true VF, a sum of true VF within individual RIs, and on the y-axis is the sum of DLVF map in the corresponding RIs. And as you can see here, they have a decent correlation. And once we break it down to see how it performs with different motion amplitude and frequency, we can see that both the motion amplitude and frequency have a very small impact on the R-square and the slope of our DLVF. Now again, we do this, we can see the similar results for different scanning KV and MAS. So again, on the left, we can see that the x-axis is again the sum of VF within RIs, and the y-axis is the sum of DLVF in corresponding RIs. And again, they show decent correlation. And for the R-square and the slope with different MAS and KV settings, we can see that the DLVF still holds reasonably well under different scanning protocols. so since the DLVF have decent performance, we decided to put it into the actual deformable motion compensation. So since it's a neural network and it's fully differentiable, we developed a gradient-based deformable autofocus framework. So we start by taking the RIs from the motion coordinated reconstruction, and then we solve the RIs independently. So to enable the back propagation of the gradient from the DLVAF, what we did is we used the partial angle reconstruction, or PAR for short. So as you can see here, we have 6 partial angle reconstructions, and our assumption is that within each partial angle reconstruction, the motion is rigid and constant. And therefore, we can assign each rigid motion trajectory to each of the partial angle reconstruction as shown here. So once rigid motion is applied to each of the partial angle reconstructions, we will sum them together to form a motion compensated image, which will then be fed into the network to calculate the DLVF value. And this whole big pink box is done in the PyTorch tensor environment, so it's fully differentiable, and we can just backward propagate the gradient to the motion trajectory to get our motion estimation. So once we've done that for all the RIs, we'll simply assemble them together to form a motion vector field for the entire volume. And then we'll add some smoothing to this motion vector field, and we'll convert it to 4 dB spline to again enforce the smoothness and diffeomorphism. And then once we got this 4D motion vector field, we'll put that together with the motion property data into our warp back projector to finally get our motion compensated reconstruction. So to test this workflow, we put that into both the simulated data and the clinical data. So here's the results on the simulated cases. On the left, we have the graph of all the results aggregated from all the testing cases. So on the x-axis, we have the SSM value of the volume before motion compensation reference to a motion-free scan, and on the y-axis, we have the SSM value after motion compensation. And as you can see here, all the point falls above the unity line, suggesting that after motion compensation, the image quality has been improved. And for more concrete example, you can see in the middle, we have 2 example cases, one with slow motion, one with faster motion. And in both cases, you can see that the vessels as well as the catheters has been restored to better shape, and the image looks more closer to the motion-free scan. And here is our first clinical case, which has a mild motion. So hopefully you can see that indicated by the blue arrow here. This contrast enhanced vessel has some motion streaks around it, but after motion compensation, the streaks has been reduced. And if we take a 3D render of the high contrast contents inside this image, we can see that the catheter has been put back into focus, and also the vessel's continuity has been restored. Here's another case with moderate amount motion, and again indicated by the blue arrow. Hopefully you can see that the tip of the catheter has been blurred by the motion artifacts, but after motion compensation, the catheter tip is clearer to distinguish. And if you again, we take a 3D render of all the high contrast content inside this volume, and then we can see that the catheter tip is put back into focus, and some fine vessel structures has been restored. And again, here is the final case in our clinical study. This one also has a moderate amount of motion. As we can see here, not only the contrast enhanced vessels are not in focus, the deposition of chemicals inside the liver is also blurred. However, after the motion compensation, we can see that both of them has been put back into focus. And another thing to notice here is that the air bubbles inside the guts has also been put back into focus. And again, we will take a look at the 3D render of the high contrast content inside this image, and we can see that the bottom of the catheter is more in focus, and a small vessel that previously cannot be seen is now back in focus, and we can clearly observe it. So in conclusion, we developed a context-aware neural network called CADLVF that can recreate the VIF value without a reference image. So the CADLVF performed decently under our testing conditions with different motion patterns and scanning protocols. And based on its fully differentiable nature, we also developed a gradient-based deformable motion compensation framework. And in our MOCO experiment on simulated cases, it showed good performance by increasing the SSM value about for about 10% averaged for our cases. And in clinical motion compensation, it includes the visibility of vessels and catheters. So our future work, including to modify our training strategy to include more data, and we try to isolate the effect of motion and the noise. And also we want to include larger variation of anatomies and possibly some common pathologies. And also we want to include a more realistic motion field. And we are also working on a fully differentiable back projector so that we don't have to rely on the partial angle reconstruction assumption anymore. So that's my talk. Thank you very much. And I'm happy to answer any questions you have.
The paper is open for questions. I have one for you.
Yep.
You're looking for a fully differentiable back projector, but actually respiratory motion is not differentiable. You have sliding along the rib cage and the spine. Would that be a problem in real data?
Oh, you mean so the motion happening in real data may not be fully differentiable?
It's not.
Yeah.
In the Plura, you have sliding. That's actually.
Yeah. Well, that's definitely something we can working on, and also like currently we are using some assumptions about the like locally rigid motion, so that so we can still use that assumption by assuming some rigid motion inside RI. So it may not be very realistic, but once we interpolate it into the 4D and smoothing it out, it hopefully can create a smooth motion vector field. So I think the point here is that we just want to avoid the partial angle reconstruction, but we are still using the rigid motion assumptions. So that hopefully that can take care of the undifferentiability of the motions inside the clinical data.
And actually, do you see any artifacts like in the spine? Because in the vector field that you showed, it was overlapping the spine. So I'm wondering if you had some, like if you introduced motion artifacts in static regions with the motion compensation.
Sorry, can you repeat?
Did you introduce motion artifacts in static regions because you estimated a motion where there is no motion?
Oh, yes. So basically, when we simulate the data, we randomly put the motion vector field inside the body. So the point here is that we want network to learn what is real appearance of anatomy rather than so that it can be aware of if this reconstruction is correct. So actually, we want to kind of add motion artifacts to the static region so that the network knows that that is not the correct answer. So it will try to avoid that as well. And also we'll learn what is the correct representation.
I have a question.
Yeah.
So it seems that the motion model, the true motion that you're dealing with seems very complex.
Yes.
And in order to get the almost artifact-free image at the presence of motion is quite challenging because that demands accuracy of the motion estimation so accurate, right?
Yeah.
I wonder if you are also interested in taking a little bit of shortcut to deal with the residual artifact on an empirical way, rather than pursuing accuracy of that motion estimation and compensation, which I like that approach and the mindset, but still there might be some way to deal with these residual artifacts in a image processing fashion or something. What do you think about that?
Yeah, thank you very much for the question. So the first thing I would say, this motion vector field estimation is really hard. So that's why we break it down to partial angle reconstruction ROI based. Actually, we have another project developing in our lab. It's purely image based. So basically, you have a motion copied image, and you just use that image, put in the network, and you generate some motion-free image. And I think there has been other work on this, probably in the neurology scans. But I guess the point here is that we are a little bit skeptical about that because it does not ensure data consistency. So like some features may be removed or some features may be added. So that's why we go with this approach so that we can ensure, everything is authentic. We are not creating any crazy structures, removing some stuff.
Great. I respect the spirit.
Yeah, thank you.
If there is no other question, I think we can move on. Thanks
Thank you
again.
very much.